Good morning. Welcome to the lecture on cable dynamics. Both lectures today will deal with cable dynamics. In addition, there will be at the end of January, in the last lecture of this semester, a lecture on bridge dynamics. But since stay cables are a very important part of cable-stayed bridges, and since they are rather sensitive, as we will hear, against vibrations, I thought it proper to distinguish the dynamics into stay cable dynamics and bridge dynamics. Today we will deal with the cable dynamics. After some general remarks, we will discuss the fundamental parameters like eigenfrequency, eigendamping, drag factors, and then we will go into the important part of dynamic excitation, where we have galloping as most important and potentially catastrophic, going beyond all limits. And then we have also like static load cases, which are of limited amplitude. Those two are from external wind sources. And we have also internal dynamic effects from acting together beam and cables. Finally, do not despair after you have heard about all these difficult excitations. There are ways and means to suppress them by using damping in different forms. So that's what we are going to talk about today. We start with some general remarks. Dynamics, bridge dynamics, cable dynamics are a highly specialized field. Practical engineers like myself, if they have to deal with a major bridge, they employ a specialist for that. One of the outstanding specialists in the world is Dr. Imre Kovac, who was a colleague of mine for many years, with whom I have done most of cable-stayed bridges I have been working on. I've been working with other in the US important specialists, Alan Davenport from South Africa, who introduced certain new things, and Bob Scanlon with the Scanlonian derivatives. Outstanding people, but in general, I just say we regular bridge engineers do not know enough to do detailed bridge dynamics, dynamic analysis ourselves. But we should understand enough to be able to follow what the specialists say and have a view and say, okay, they have looked into everything, what they propose is reasonable. I remember when we first had Alan Davenport giving his expertise on the Sunshine Skyway Bridge in the US, and he talked about the basics and half an hour, and I know myself and my colleagues, we were sitting, we didn't understand a word. Today I would understand more. But so what I'm trying to tell you here is not how to do a dynamic analysis and proof of a, say, cable-stayed bridge. That's far beyond what I'm talking. But you should understand the basic phenomena. What means galloping physically? How does it come up or later flutter for the bridge itself? And what are the possibilities to calculate and the damping possibilities? So you should be able to understand what the dynamic specialists later will tell you. That's what I'm after. And as I say, Dr. Kovacs is an outstanding, he's a bridge engineer that has specialized on dynamics. And since I know my limitations in this field, I have asked him, we've worked together for 30 years, to make this part of my lectures the dynamic part, and he was kind enough to accept. And I think what he has put together, especially in the script and of course also in the book, is about the best there is in summing up what can be said for general engineers on dynamics. So I'm very thankful for him. And now I try to tell you what he has told me. In order to make you aware that we are not just doing some mathematical, artistic up in the air. We're talking about real danger. We will show a little movie with an oscillating cable. This is with light rain and light wind. It is rain-wind induced vibrations on a bridge, and you can see, well, you can see, you can't see very much, I'm afraid. It was just, of course, it's the Houston Ship Channel Baytown Bridge, which we see in great detail. There wasn't very much wind, but this was enough to heavily oscillate the cables, which can damage the anchorages and which can damage the cables. So we're talking here of a real problem which can occur if we don't look out for it. Here we go. Now, very important, stay cables have very low internal, say, natural damping. What we have done here, we have measured the decay of a stay cable at that time of the Pesco-Kennewick Bridge, and we could show in a mathematical formula, very typical, how the decay curves runs, and here it was e to the power of minus 0.012, and now here we have something which is often not understood, the logarithmic decrement of damping. We know logarithm is something to the power of, and the logarithmic decrement is the power to which e has to be risen to show the decay curve. So 0.012 is in this formula the decay formula. So that's important basically that you know that's not something in the air. It just indicates how the cable decays when you start by hand or with a rope and the cable oscillates, and then you measure how the amplitudes become smaller and smaller, decay with time. Here after 120 cycles was only 20 millimeters. We started with 80 millimeters. And this, I recall, decay is given in an E function, and the logarithmic decrement is the power to which we have to take E. Now, 0.012 is very small. It's something like a fifth, a sixth or something of regular steel structures. And that has to do that we have stressless deformations here. When a cable deflects, it basically doesn't change its stress, and the force which brings it back are just the radiating forces from the tensile force. If we bend those, then we have forces which try to get the cable back. But it has not to do with inner workings. And that's why we here, because it's a geometrical stiffness instead of a structural stiffness, we have very low damping values, the lowest in practical engineering there is. That's why these cables are so sensitive against even small wind forces. So that's what you have to keep in mind. Geometrical stiffness, very low damping, 0.01 or something as the defined logarithmic decrement. The second important point why these cable vibrations are dangerous has to do with the second order effect under tension. I have shown you in an early lecture the formulas how this works. In principle, it is like this. If I have a cable which, say, 200 millimeters has a certain stiffness, and if I then have this cable and I deflect the beam, then the cable, there will be a deflection between the cable and the anchorage, which, okay, it's very small, but this change of angle and the stresses from that is increased many times by the tension which acts at the same time. It says here, if we have first order theory non-linear, then we just have a certain radius here, depending on the stiffness, and certain stresses. However, if we have a tensile force, then this radius becomes much smaller. It's pulled together, so to say, and this nonlinear effect due to bending and tensile force increases these stresses considerably, and it's in the cable sizing a condition to keep that low and so on. So fatigue due to high bending stresses from nonlinear theory, tension and banding is dangerous. Those are the two basic characteristics which are, so to say, unfavorable. Low damping, internal damping, and the increase of bending stresses from cable oscillations due to nonlinear theory. For the bridge, the stay cables exert wind loads. You see, if we have the cable stayed bridge and the wind is blowing transversely, then the static force which acts on every cable over its full length, of that one half goes to the tower and the other half goes to the beam. So the beam has a wind load not only from the beam itself, but also from the lower half of the stay cables. And the interesting thing is, if we increase the span somewhere typically in the range of about 800 meters, the bending moments in the beam, the transverse bending moments from wind transversely, are bigger from the loads on the stay cables than on the beam. So it is an important factor for transverse bending. The wind load on the stay cables, which is transferred to the beam. First, for short spans, most load on the beam comes from the beam itself. With increasing spans, that is a bigger part, and somewhere above 800, 900 meters, generally the wind loads from stay cables are higher than the wind loads of the beam itself. So it's an important sizing parameter the wind load from the cables on the beam. Now, how can we then, or we try, to reduce these wind loads on the cables which act on the beam? Now, first of all, the wind load is some wind speed squared with a constant times the diameter of the stay cable times a shape factor. The wind speed is given, so we can vary the diameter and the shape factor. Now, with the diameter, one has, of course, tried with time to reduce the cable diameter as much as possible. It started with a large distance between, say, the parallel strands or wires for some corrosion protection. Then compact stay cables were tried, where this is more or less directly extruded. And with the wires, it can even be, because these are fabricated on site, we cannot make these too tight. We have to thread in the strands. But if we use completely shop fabricated high M parallel wire stay cables, then the PE pipe can be directly extruded very tight. So in practical terms, for big bridges, maybe 20 years ago, there still were, say, 300 millimeter diameter stay cables. And they are now reduced to something like 200 millimeters. So what has been done there to reduce the drag has been done. The next question is the drag factor from which for a circular cross-section. And there it is interesting that that's not just some constant value. We have here the C factor, and we have here the Reynolds number. Now, the Reynolds number, I've often told you, it's basically the wind speed, however, times the diameter of what we are talking about, divided by the kinematic characteristics of the air. That's a constant. And if we use stay cables, then we can give this factor as a cable diameter, which is much more helpful. And we see we are here, say, 5 centimeters, 10, 15, 20, and so on. Now, the interesting thing is, you may or may not recall, I've mentioned it several times, Reynolds to the power 10 to the power of 5 gives a change of the internal characteristic of the wind from laminar, just steady, to turbulent, which vortices and all that. And that's always a very important point in all bridge engineering, this Reynolds factor of 10 to the power of 5. And you see here, for low Reynolds numbers, or make it easier for small cable diameters, we have a drag factor, I just go to this line here, in the range between 1 and 1.2. And suddenly, in the range of Reynolds to 10 to the power of minus 5, which is somewhere 10 centimeter diameter stay pipe, this thing drops to, well, you can find here 0.5 or so. There is an important drop. Now, it means for us, since our stay cables are hardly less than 10 centimeters, if we have lock coil ropes, there may be smaller ones, but then the diameter itself is small, so the forces are not so big. For the diameters we use up to 10 centimeters, we can use low factors which are codified. These are some old codes here in that range, somewhere between 0.5 and 1.2 as a drag factor. I go one on. And so if we now say, okay, we accept from these various code regulations all over the world, we accept 1.2 up to, I say, a diameter of somewhere 10 centimeter of a stay cable. That's easier to understand than the Reynolds number here underneath. And then we accept, well, 0.7 to 0.8. The codes vary there a little bit. So that's the drag factor. That's a natural constant. I just point out here an interesting phenomenon, which we will come up later. We can further reduce the drag factor, meaning the resistance a cable has against the wind, by profiling the surface. And in the first moment, it sounds a little strange. How can you, if you, so to say, roughen the surface, how can the drag factor, the resistance, go down? But it does, because there is a change in the internal structure of the wind, which, if that's the cable comes and goes around, and the vortices are further pulled out. The point where these two go into two pieces is further to the leeward side. And if somebody of you plays golf, then you may know that the later golf balls have little dimples on their surface. And these dimples reduce the drag on the golf balls. So the same hit gets you further away. And that's the same here. It's also called a dimple. And you see, if you have we will later see a picture, dimples on the surface of a pea pod, you see you're definitely below the standard curve for smooth surfaces. And there are other possibilities, ribs, and so on. We can do something there. We will later. So these surface treatments have two purposes. On one hand, they at least do not increase the drag factor, they reduce it a little bit. But the main thing is they prevent a certain dynamic effect, wind, rain, induced vibrations, which we will come up later with. I just wanted to point out to you, when I talk later, we can change the surface, that you say, well, but then the drag is much higher. No, sir, it's not. That's a very favorable kindness of nature, so to say. Okay. Of course, whenever we start to calculate anything with cables, the first thing we need are the eigenfrequencies. Very simple. We just have basically to remember the eigenfrequency of a cable is proportional, first of all, to the square root of the cable force. The more taut a cable is, think of a violin. When you pull that, the faster it will oscillate. That's very simple. And on the other hand, it's indirectly proportional on the length. That's also, I think, we have a feeling when the cable becomes longer and we start to push it up and down. So that's very simple. That's the first eigenfrequency, which I think in 95% of all phenomena in dynamics, we only deal with the first eigenfrequency. The others are an octave higher, we know all that, but they are linear. But just remember, proportional to the square root of the tension and indirectly proportional to the length. Now, we come to the dynamic excitations. And there we have, in a very general way, not only for stay cables, but for all dynamic phenomena on buildings, to distinguish between catastrophic events, which can go beyond all limits and basically destroy the structure, be it a cable, be it a bridge beam, be it a lamppost or a high-rise building. So there are some nonlinear effects, and we must understand how the energy required to destroy a structure is taken out of the airstream. Those are the nonlinear catastrophic things. And then there are other which are more static in its nature. That means we get deformations or cable oscillations, but they are limited. It's basically a static load, not going beyond all limits, pulling more and more energy out of the stream like the catastrophic, but more a static load which gives a limited oscillation or deformation. Those two are from outer wind sources. There is also internal damping. We don't need wind for that. That has to do if the eigenfrequencies of the beam and tower and the cables are in certain relations, 1 or 2. That's what we basically have to discuss in dynamic excitations. And we start with one dangerous and not yet fully understood, basically the galloping, but the most important then is the rain-wind induced vibrations. Now I want you to understand that's rather important that you understand the phenomenon of galloping. The curve you please remember is this one. We have here the wind direction, the angle in which the wind blows, and we have here the lift factor, which from this wind pushes upwards and downwards a cable. And normally this is linear. If we have wind blowing from below, the cable is pushed upwards. If it goes to 0, there is no uplift coefficient. And if it goes on positive, it pushes it down. That's for a round cable, linear, nothing special. And the one important thing in dynamic cables here is if we have a somewhat deformed cross-section, not just round, and it can be rather small deformations, I'll show you, then we get a phenomenon that is not linear anymore, but we have a change in the direction of the lift factor, meaning if we come from a windward, the wind blows, say, from below, we push up. If we come closer, there is a nonlinear increase, and then comes the critical point. If we change the direction, then also with nonlinear increase, the lift factor changes its sign also. And with this phenomenon, it's the first derivation, dc after d alpha, first derivation of the C function. Negative, this is rather high here. That is the phenomenon which enables the oscillating cable to pull energy out of the wind and thereby then increase. And you have to be aware that we have two speeds here we are talking about. We have, say, horizontal or slightly inclined, but I just take the horizontal wind speed because that's what it's governing. Horizontal wind speed, and we have an oscillating cable. And we have to sum up vectorially the two speeds, this speed and that speed, so we get an inclined speed, that's this alpha here, which is the combined speed of the wind and the cable. And the more the cable oscillates, the bigger the vectorial sum of the speeds is, and the more wind is, when going upward, the lift factor is upward. And when we go downward the cable, the lift factor is downward. And this always increasing upward, downward, more downward. That's the mechanism with which we pull energy out of a horizontal wind, not for a circular, but for somewhat deformed in transversely to the wind longitudinal. That is a galloping phenomenon which we can see quite often. And we have here a rather rough ice on a leeward side of a cable, which can happen. Much more pronounced, this phenomenon is for transmission lines, overland, the high voltage electrical cables. There we can see more often ice really hanging down. And from this phenomenon, I'm not saying you would be lucky to see it, but you could, on a walk, on a winter's day, you could very well see, it's not so rare, that these cables swing wildly up and down with the ice on. And that's ice galloping. Naturally, once they oscillate enough, the ice falls down and the phenomenon is gone. It doesn't hold on for a long time. But there you can see it more often. Now, a special case of deforming a circular section to something where the wind can hold off is so-called rain-wind-induced instability. What happens is that with light wind speeds, now 10 meters per second, times 3.6 is 36 kilometers, if that tells you more. It's a lower wind speed. And rain. We have the phenomenon that at the top side, a little bit to the leeward side, and at the bottom side, the rain just doesn't run away, but forms small rivulets, small little rivers of water up here and down here, which the raindrops are kept in place by the wind which goes around the cable and exerts certain forces. And these little rivulets apparently are sufficient to cause galloping, important galloping oscillations. What we've seen here in the first movie were galloping oscillations, light wind and light rain. And you saw the cables were going up, down a meter. So it's an important phenomenon. Remember, low wind, little rain, forming rivulets which make from the circular shape some deformed shape where the wind then can get hold. The thing is, I always say, rather new. When I started doing cable-stayed bridges, it wasn't known in the 70s. And then somewhere, somebody in Japan detected it and investigated it. And then I said all the other stay cable bridges learned from it and also applied it. It's a phenomenon which came up in the last 20 years. Well, it probably has to do that cable-stayed bridges have become, first of all, longer spans, lighter, and so they are more sensitive. But this phenomenon wasn't known 30 or 40 years ago, and it's not fully understood, and I'm quoting here Kovacs. It may not be surprising if I don't understand it completely, but Kovacs says he doesn't understand it, or nobody really fully understands it today. So there are still some uncertainties. But the phenomenon is there. I've shown you the movie, and there's another one later. Now, excitation parameters are the cable diameter itself, the wind speed, the wind direction, and the rain intensity, for example. In addition, if we look closely in the laboratory, and it was quite a success that after many years of trying, it had been reproduced in the laboratory. Because that was one of the puzzling things initially. You saw it on the bridge. Beautiful. In the laboratory, put the cable on with the same dynamic characteristics, wind, and have the wind machine on, the rain. You couldn't reproduce the darn thing. So this was really and the Japanese succeeded for some time, and then they saw that in addition to forming just the rivulet itself also oscillates. And there may be something in which is mathematically difficult to take out. So our friends Miyamata, Yamaha, Hoyo, and Shiraishi in Japan, they were the first ones to reproduce the phenomenon in the laboratory, and found out, again, it's quite diameter dependent, difficult to understand, up to 200 millimeter diameter. This change in the run of the uplift, first derivation of the uplift formula, is about minus 1.5 for a wind speed of 10 meters per second. If we go thicker than 50 meters per second, these are all very things which have been watched in laboratory. One doesn't have a full theory. Okay, well then Freycinet made also tests in Japan and came up, if he then multiplies the speed with a change in lift, then he said, okay, for a cable there between 10 and 15 meters per second wind speed, we had a certain change in uplift, and below 7 meters there was nothing, above 20 meters there was nothing. In addition, of course, they showed that the Freycinet dampers naturally are the best. This was the amplitude without damping, and the amplitude was reduced to this with Freycinet dampers. So, again, just to show you, it's a real phenomenon. This is the rubber ring at the tip of the steel pipe, which is cast, say, into the concrete, and the stay cables run in, and this is a rather hard neoprene ring. It was for the Baytown Bridge. I've done it, I know it. We had some problems there. And you see, after a heavy attack, say, of wind, rain-induced vibrations, which you saw on the first movie, these neoprene rings, and we've seen it with other bridges, they are worked so hard that they become hot somehow, and they start to be liquid in a way. You can see it here. It's like having heated them up. And so they are destroyed. And other things too. It is a phenomenon, although we don't fully understand it, we have to be on the lookout. And now we will go to the next movie. I agree, it's a little unattractive theme. Okay, this is now in Japan. Also, probably just with a handy camera, I take it, from a moving car in the rain, so the quality isn't good, but you can see how the cables vibrate. And here you have the problem at the anchorages, where the neoprene boots are being pulled out. just see how wildly they go about. And it's obvious, generally, there are always groups of cables excited at the same time. Groups of cables with similar eigenfrequencies and so on. Not all the cables all the time, but different groups at different times. Here you see again, there's already the highway patrol, how hard they act. So, now, this was the first part where I have concentrated basically on the basic parameters and on the most dangerous phenomenon, wind-rain-induced vibrations. I hope with those movies I've made you aware that we are not talking just some philosophical mathematics in the air, as I said. It's a real problem which can destroy or severely damage stay cables. And we have to be on the watch out. I've shown you the mechanism, tried to show you, the mechanism by which the cable system draws energy out of the horizontal wind. It draws energy out, on one hand, by changing the relative wind direction, relative from adding up horizontal wind with the actual vertical velocity of the oscillating cable, so that we get a change in overall relative wind angle of attack. And on the other hand, that we have this phenomenon, which is depending on the cross-section, that we have a change in the lift factor from going up and through zero going down. And because in the moment where the cable goes up, it's pushed up by the combined wind speeds. The moment it comes down, goes through zero, the sign of the lift changes to compression. So while going up, it's constantly pushed up. While going down, it's pushed down. And you can imagine, even if it's a small force, if applied in phase, always at the right moment, you can increase the amplitudes theoretically beyond all limits, or, as you've seen on the movies, in the meter range. Okay, thank you.